Okay, we've gone through a few problems where we've drawn a chair conformation and we've done the ring flip structure to draw another chair conformation, and we want to figure out which one is more stable, what the energy difference is between those, and also if we wanted to calculate the percentage in one conformation over the other, we need to know how to do that. So I've given you the first chair conformation with all of the substituents in there. The first thing we want to do is feel comfortable with ring flipping this structure. So I would number it first, and I would also draw in the hydrogens that are missing. That way it's very clear whether something is axial or equatorial, or whether it's pointed up or pointed down. We have a hydrogen here, we have one missing here, one here. So every carbon that has a substituent on it, I would draw in the hydrogens. Now let's ring flip our structure. And before we do this, what we want to do is number our structure. Remember, it doesn't matter where you start numbering as long as you're consistent. So I always number clockwise, and I'll do that. So this will be 1, 2, 3, 4, 5, 6. And then let's draw our other chair conformation. So we know this is in equilibrium with this structure. Okay. We also want to number this structure, and since we numbered it clockwise in the first one, we need to do the same thing in the second structure. Now, when we're figuring out where number 1 starts, we're going clockwise and 1 carbon over. So 1 will now be here. We have 2, 3, 4, 5, 6. So we started at this carbon in our first structure. When we ring flipped, we went over here to number 1. Now we can draw in our substituents. So on carbon 1, we notice that our methyl group is going up. It should still be going up in our ring flip structure. The only difference is it went from equatorial and now it is axial. All right. On carbon 3, we also have another methyl group going up. Let's erase this. We don't have a hydrogen. So this should be methyl. And then on carbon 3, we have the same thing. We have another methyl group that is going up. Notice again that it went from equatorial in our first structure to axial. So every time we do a ring flip, it should go either from equatorial to axial or from axial to equatorial. But if it's on top, it should stay on top. If it's on bottom or pointed down, it should stay on the bottom. Okay. Next one, we have our tert-butyl group going out to the side like this, which is now equatorial. All right. So we have all of our substituents on. If you want, you can also put in the hydrogens. Let's practice also going from the ring flip structure to the flat structure. So you want to be able to do that, or go from the flat structure to the ring flip structure. What would this look like if we were to draw this flat? So if we draw our 6-membered ring, and 1, 2, 3, 4, 5, 6. Remember that if we have a group pointed up or on the top in our chair conformation, it's going to be on a wedge in our flat structure. So this methyl group is pointed up. It should be on a wedge. On carbon 3, our methyl group is also pointed up. It should also be on a wedge. And last, on carbon 4, we have a tert-butyl group that's now in the equatorial position, but it is pointed up. It should also be on a wedge. So you want to make sure you can go that way, and you want to make sure you can go the other way from the flat structure to the chair conformation. Now, we need to figure out which conformation is more stable. And remember that the Gibbs free energy, or these A values, tell us the difference in energy between that substituent being in the axial versus equatorial conformation. And we know the types of strain that contribute to this are 1,3 diaxial interactions or gauche interactions. So since these are additive and you'll always be given the Gibbs free energy values, we can just add these up. We're going to look at each substituent and figure out, is it going to something that's more stable or something that's less stable. So let's calculate the total difference in energy between the two conformations. So I'm going to start here on carbon 1. we see that our methyl group is going from equatorial to axial, right? We know based on the interactions we've talked about that this is unfavorable, so we're going to have a positive delta G value for that one. That will be 1.74 kilocalories per mole. And again, you'll be given these values. All right? Let's look at our next substituent. Here on carbon 3, we have another methyl substituent that's going from equatorial, which is more stable, to axial. So will also be a positive delta G value. In the last substituent, we have a tert-butyl group here going from the axial to the equatorial position. So that one is actually going to a more stable conformation. This time we're going to use a negative value since it's going to the equatorial. So we're going to subtract 5.0 kilocalories per mole. And this will give us our total going from the conformation on the left to the conformation on the right. So if you plug that into your calculator, you get negative 1.52 kilocalories per mole. Okay. What information does this tell us? This tells us that there is a much stronger preference for the tert-butyl group going to the equatorial position. So the preference for that is even greater than two methyl groups going from axial to equatorial. So the tert-butyl group is so large that it outweighs the preference for two methyl groups going to the equatorial position. Okay, so this structure on the right will be most stable. And the reason we know this is because our total Gibbs free energy that we got is a negative value. Right, so that will be the preferred structure. Anytime we're being asked to calculate either a percentage in one conformation, we always need to calculate the equilibrium constant first. For the equilibrium constant, we know that delta G is equal to negative RT ln of K. Okay, so in this case, let's say that we want to calculate the percentage in the most stable conformation. So since we are calculating the most stable conformation, we have to make sure the number that we plug in is the negative value. So that will be negative 1.52 kilocalories per mole is equal to negative right? So R is a constant. You'll also always be given that value. You don't have to memorize it. We're going to say this is at room temperature, so 298 Kelvin, natural log of K. Okay, so the next thing is we have to solve for K. So K is going to be E to this whole thing. We're going to have the negatives cancel out, 1.52 divided by 0.001987 times 298. So this whole thing. Once we calculate that, we get K, our equilibrium constant, is equal to 13.0. And I always put this over 1 to remind ourselves that this is the concentration of products over reactants. So that means at any given time, for every 13 molecules that are in our conformation on the right, the most stable, we will have one molecule in our least stable conformation on the left. So all it is a ratio of these two. Okay. Next thing, so if we want to calculate the percent in the most stable conformation, we're always going to take the part over the whole. So in this case, our part, since we're talking about the products, our most stable conformation on the right, we want to take 13 divided by the whole. So 13.0 plus 1, since it's a percent, we'll multiply by 100%. And if you do this, we get 97%. And one way to check yourself is if it's in the most stable conformation, it should be a high percent. It has to be higher than 50%. If we were to calculate in the least stable conformation, or the conformation on the left, we would have 1 over 13 plus 1 times 100%. So I'm sorry, this number should be 93%, and this number should be 7%. Okay, so you want to be able to calculate both. Make sure you pay close attention to which conformation you're calculating the percentage of.